In the chem activity number 12 and the corresponding video, we will explore mole-mass relationships in the context of aqueous solution chemistry. Now, this concept or this topic is crucial to understanding chemistry because a lot of chemistry happens in aqueous solutions. So any time invested here to ensure that you understand the nature of making a solution and the corresponding calculations will prove to be helpful for the rest of this course, that is this semester and even into next semester. Let's first of all look at what's involved in taking a solid crystal and dissolving it in water. So I'm going to show you a little bit of an animation. Now, full disclosure, I made this animation about 20 years ago when Flash software became available and was popular. And I really like the idea of trying to make something to help students see what might be happening at the molecular level. So the simulation is rather amateurish, but hopefully it'll give you some ideas. So here we're going to look at the dissolving of an ionic compound. And so here are some common ionic compounds: sodium chloride, magnesium chloride, and aluminum chloride. Now, one of the things that I'd like to highlight here is, and this is supposed to be representing sodium chloride, that when we write sodium chloride, we're actually thinking in terms of a solid as this crystal lattice. And for every one cation, there is an anion. And these exist, as I say, in this beautiful crystal lattice. In order for this crystal lattice to dissolve in water, the crystal lattice has to be completely broken apart. In other words, we have to break the ionic bonds that are holding the cations and the anions together. Also understand the crystal lattice is three-dimensional, though it just looks two-dimensional here. The other thing is you'll notice that I'm trying to show the beaker of water with the water molecules in the background and that they're in constant motion flowing over one another. And they're very much involved in the dissolution process. So let's watch how the crystal lattice breaks apart. So this would be the act of dissolving, the crystal lattice breaking apart into the cations and the anion. The corresponding equation would look like sodium chloride producing sodium ions and chloride ions. I want to highlight that for every one sodium chloride unit, so it's not a molecule, we can call it a formula unit. For every one sodium chloride unit, one sodium ion is produced and one chloride ion is produced. We can also talk about it at the level of moles. For every 1 mole of sodium chloride formula units, 1 mole of sodium ions are produced and 1 mole of chloride ions are produced. So that's the context of sodium chloride dissolving. Let's look now at what happens when magnesium chloride dissolves. So again, the crystal lattice entering into the water. And one of the things that perhaps you notice is for every 1 magnesium chloride formula unit, there's 1 magnesium ion that's produced and 2 chloride ions that are produced. And again, I'd like to highlight the idea that even though we might talk about that we have a certain solution of magnesium chloride, there isn't actually any magnesium chloride in that solution, at least not any units of MgCl2. It's all in the form of magnesium ions and chloride ions. But do keep in mind, again, the stoichiometry. For every 1 MgCl2, there's 1 Mg plus 2, and there are 2 Cl negatives. Finally, let's look at what happens when aluminum nitrate dissolves in water. Perhaps now you're getting the idea. The crystal lattice has to break apart. And again, for every 1 aluminum nitrate unit, we have 1 aluminum ion that would be produced and 3 nitrate ions that are produced. So the stoichiometry is inherent in the formula, the ionic formula of the ionic compound. Let's move on in terms of the notes. So here's a diagram representing that dissolution process. And note I show cations and anions. This well could be the sodium chloride crystal lattice breaking apart. The water solvent is very much involved in this dissolution process. And you may remember that water is polar and in a sense has a negative side and a positive side. So around the anion, the more positive side of the water molecule will surround that particle. And around the cation, the more negative side of the water molecule will be surrounding that particle. The equation is written as NaCl, that is one NaCl, will produce one sodium ion and one chloride ion. Note that although water is involved in this process, we don't know the exact number of water molecules, and therefore it's not included as part of like a balanced equation, but rather we write aqueous to indicate that water is involved and we produce these solutions. Now, I'd like to talk you through the preparation of a solution using a volumetric flask and the kinds of calculations that are necessary in terms of coming up with what the concentration is in units of moles per liter. To do this, I'd like to use the example of magnesium chloride. So we're going to make a magnesium chloride solution. You can see the balanced equation at the top. So for every one magnesium chloride unit, there's one magnesium ion that's produced and two chloride ions that are produced. Let us say that we measure out 10 grams of magnesium chloride and we've quantitatively transferred it to our volumetric flask. We're going to use a 250 ml volumetric flask. So the idea then is we're going to add enough solvent, in this case water, to bring the level up to the mark on the volumetric flask. It's important to highlight the idea that that 250 ml solution, well, that's actually the volume of the solution. It's not the solvent. Note that the total volume, that is the total volume of our solution, is made up of both the solvent and the solute. So what about the calculation in terms of coming up with the concentration? Well, if we did measure out 10 grams of our compound, well, we can very easily calculate that this is equivalent to 0.105 moles. So we take those 10 grams and divide by the molar mass, or times 1 over 95.210 grams. And we end up, of course, with 0.105 moles to 3 significant figures. So that's the amount. Note that we say magnesium chloride formula units. That's what Fu apostrophe S stands for, because technically these are not molecules. You could just say units, or you could just say 0.105 moles of magnesium chloride. So now to determine the concentration, which we sometimes refer to as the molarity, and note we can abbreviate all of that by putting square brackets around the magnesium chloride. So this means the same thing. That is, the square brackets means the same thing as the concentration of magnesium chloride. And we calculate that using the amount of magnesium chloride in the units of moles divided by, and be careful here, the volume of the solution, not the solvent, but the volume of the solution, and in the units of liters. So the calculation would look something like this: 0.105 moles divided by 0.2500 liters. So note, I've taken the 250 mils and divided by 1,000 to get the volume in liters. So then the concentration would equal 0.420 molar. So that's capital M, or you can also write moles per liter. So that's the calculation involved in coming up with the concentration for a solution. That's something I'd expect you to be able to do in the lecture portion of the course, but I'd also expect you to be able to do this in the lab. So this calculation is quite important and quite universal in that you will need to do it often in various parts of the course.